Hello. Today we are going to expand on what we know about roots of polynomials and how they relate to one another. So, first of all, I want to remind you that roots are also the zeros of a polynomial, and we can find them in that form x minus a. So when we see x minus a, that's a factor. It gives us a root and it gives us a zero. So a is the zero. Um, this is the factor, so forth and so on. So let's look at how we can use this to find possible solutions. So if we're looking for where p of x equals 0, that means we're looking for our x-intercept or our 0 to our solution. And so one way to do this is to graph it. And if you look at this graph, we can see that there's that solution right there at 4. But let's say you don't have a graphing utility. How could you find that? Well, the rational root theorem says that you can find any possible rational root by taking every factor of the last term, and we're going to call that p. So p is our constant, and q, which is going to be our leading coefficient. And we'll find all the factors of p. So the process for using the rational root theorem is find all factors of p, and then you're going to find all the factors of q, and then you're going to look at all the combinations of p divided by q. So if we look at this equation, our p is 4. So all the factors of 4 are 1, 2, and 4. And it's also the positive and negative of all of those. So plus or minus 1, plus or minus 2, and plus or minus 4. And then we have all of our factors of q. Q in this case is 8. That's our leading coefficient. And so all our factors of 8 are plus or minus 1, plus or minus 2, plus or minus 4, and plus or minus 8. So then our last step is to take all of our p's over all of our q's. And so to do that, we're going to take 1 and put it over each one of those. So 1 over 1 is 1. 1 over 2 is 1/2. 1 over 4 is 1/4, and 1 over 8 is 1/8. Then we take 2. 2 over 1 is 2. 2 over 2 is 1, and we've already got that here. So 2 divided by 2 is 1. 1's already in our list, so we don't have to list it again. 2 over 4 is 1/2. That is also already in our list. And 2 over 8 is 1/4, which is also in our list. So we're done there. Now we're going to do 4. So 4 over 1 is plus or minus 4. 4 over 2 is plus or minus 2, so that's already in our list. 4 over 4 is 1, and 4 over 8 is 1/2. So these are all the possibilities that we could have for our p's over q's, or our factors, or our zeros. So any one of these numbers could be a zero of the polynomial. And so what we find is that 4, this number that we found up here, is on our list. So it is, in fact, a 0 or a possible 0 of the polynomial. And that's pretty much how you do this. So you have to list out all of your combinations of P over Q. All right, so let's look at this more in context of a real world problem. So we have a storage company. It's designing a storage unit based on the dimensions of shown. The volume of the container is modeled by this polynomial. So what they've done there is they've taken all of these dimensions and went ahead and multiplied them out for us. And what are the dimensions of the container if the volume is 154? So in this case, what we're going to do is we're going to set 154 equal to our polynomial. And it's not evident that we can do anything like that with this. So we need to make it equal to 0. So we're going to move that 154 over. And now we're going to do our P's and our Q's. So our P is 154. And we're going to find all of our factors of 154. So we've got 1, and I'm going to actually do this old school like we were factoring before. We get 1 and 154, and 2 and 77. So that kind of clues me in that we're going to have 7 and 22 and 11 and 14, and that's going to be it. So those are all of our factors of 154. So we've got 1 plus or minus 1 plus or minus 2 plus or minus 7 plus or minus 11 plus or minus 14 plus or minus 22 plus or minus 77 and plus or minus 154. And then for our Q's, we have 2. So we get plus or minus 1 and plus or minus 2. So now we have to do our P's over Q's. And we get plus or minus 1, plus or minus 1/2. So there's 1 over each of those. 2 over 1 is 2. 2 over 2 is 1. And we get plus or minus 7, plus or minus 7/2, plus or minus 11, plus or minus 11/2, plus or minus 14, but 14 divided by 2 is 7. Same thing with 22, plus or minus 22, but 22 divided by 2 is 11. Plus or minus 77, plus or minus 77/2, and then plus or minus 154. Now, the way that we see if these are zeros, the easy way is to graph them. So I am going to now hop over to Desmos, and we're going to put in 2x cubed minus 7x squared plus 6x into our equation. So 2x cubed minus 7x squared plus 6x minus 154. And the easiest way to do this is to now look at what our actual 0 is. So our actual 0 is 5.5. And 5.5 is the same as 11/2. Now, how do we check this? The way that you check to see if a 0 is actually a 0 is synthetic division. And if you'll recall, we know that a 0 is a 0 when the remainder of the synthetic division is actually 0. So we're going to get 6 and 154. So we're going to pull down 2. That gives us 11. Oh, and that should be negative 154. 4 times 11/2 is 22. That's 28. 28 times 11 has is positive 154, and there's our remainder of 0. So our x has to be 11 halves. And we are done. So now let's talk about the fundamental theorem of algebra. The fundamental theorem of algebra says that whatever the degree of a polynomial is, then there are exactly n solutions in the set of complex numbers. So if you have a 5th degree polynomial, there are 5 roots. And those could be they could be real roots or imaginary roots. If you have a 30th degree polynomial, then there are 30 roots. That's what we got here. So this one says if we're going to find all of the complex roots, now remember that the real numbers are part of the complex. So real numbers are included in the complex set. So let's find all the complex roots. And you're going to hate me when I show you how to do this, but this is life. So the easiest way is to find all the real roots first. So to do this, we're going to once again head to Desmos and we're going to graph that equation. Okay, so there's our graph. We have a real root at -1 and a real root at 2/3. And if you're confused about the decimals, like if you get a decimal and you don't know what it is, you always go back to the rational root theorem that says p is 2. So our roots are plus or minus 1 and plus or minus 2. Our q is 3. So our roots are plus or minus 1, plus or minus 2, or plus or minus 3. So that means that our p's over q's are plus or minus 1, plus or minus 1/3, plus or minus 2, and plus or minus 2/3. Now, back in the olden days before we had really awesome graphing calculators, Miss Snow had to do the synthetic division for all of these to tell whether they were roots. Well, we know that -1 is a root. So I'm going to start with -1, and I am going to do my synthetic division to get my next level down polynomial. And so to do that, I'm just going to go through the motions here. And lo and behold, it is a polynomial. And then all you do with your next root is we're going to do synthetic division with that next root as well. So we get 2, that's 6. 6 times 2/3 is 4. 6 times 2/3 is 4. 3 times 2/3 is 2. And that gives us a 0 as well. And so now this, of course, became a, oh gosh, guys, never mind. I just did that wrong. Let me start over. What you do with this synthetic division is we're going to actually do it with the new stepped down polynomial. So we're going to use these as our coefficients because we know that this is x cubed, x squared, x, and that constant. And if this is a root, we should be able to do it with this and get our next possible root. Okay, and now here we have a quadratic. So this is x squared, x, and 3. And what you're going to do is you're going to do your synthetic division with all your roots until you get down to a quadratic or a number that can be factored. So I'm going to now factor this quadratic. So we're going to get 3 times x squared plus x plus 1. And we are now going to do the quadratic function, the quadratic equation with this. So we get negative b plus or minus the square root, b squared minus 4ac all over 2. So we get negative 1 plus or minus the square root of negative 3 all over 2, just going to give us negative 1 plus or minus I root 3 over 2. And so now we have, this is 2 roots here, and we have 2, 3, 4 roots to our quintic with 4 to the 4th power. All right, so now let's see how irrational roots relate to coefficients. So suppose that you have a quadratic polynomial who has one rational zero, c, and one irrational zero, a plus b. Are the coefficients rational? So we know that we have zeros at c, so we're going to have x minus c. And we're going to have, and I'm going to actually zoom in and give myself more room to write. So let me erase this. And so we're going to have x minus c. And we're going to have x minus a plus square root b as our two factors representing our zeros. And so now what does p look like? So what we're going to do is we're actually going to multiply this out. So we're going to have x minus c times x, I'm going to distribute out that negative, minus a plus square root b. And let's just multiply. So we have x, we have c, we have x, negative a, and square root b. So we have x squared minus ax plus square root bx, cx, negative ac, and c square root b. So what you'll notice is that there are no common terms that we can combine. So this whole polynomial is just a jumbled mess of x squared minus ax plus cx. I guess we could combine these two terms. Minus ac plus square root bx plus square root bc. But other than this, we can't combine anything. And so what happens is we have these irrational numbers here that create all kinds of havoc. And so what happens then if we have the conjugates, the conjugate pair where those are both irrational zeros? So we're going to have x minus a plus square root b and x minus a minus square root b. So what happens here is, let's distribute this out. So x minus a minus root b and x minus a plus root b. And we're going to have x, negative a, negative square root b, and x, negative a, positive square root b. So we get x squared, negative a x, and square root bx, and negative ax, a squared, negative a root b, and negative square root bx, and positive a root b, and b squared is negative b. And then what you'll notice is we have a negative right here, a negative a root b, and a positive a root b, so those cancel. and a negative square root bx and a positive square root bx, and those cancel. And so then we end up with x squared minus 2ax plus a squared minus b. But all of these are rationals. And so if you have conjugates, you're going to have rational roots. So this takes us to the conjugate root theorem. And what it says is that if you have a polynomial with all real coefficients and you have a irrational root, then the conjugate of that irrational root is also a root. So this says, let's see how that looks in practice. It says that if you have a quadratic with rational coefficients in standard form, such that it has this as a root, then that means that if 2 plus 5i is a root, 2 minus 5i must also be a root of the polynomial. So we're going to do x minus 2 plus 5i and x minus 2 minus 5i. So we get x minus 2 minus 5i and x minus 2 plus 5i. And then we're going to do our multiplication here. We get x squared minus 2x plus 5ix minus 2x plus 4 minus 10i minus 5ix minus or plus 10i, and then this is going to be plus 25. And so again, your 5ix's cancel and your 10i's cancel. And so we can combine our like terms. So we have x squared. We have negative 2x, so that's going to be negative 4x plus 29. And there is our polynomial. And what would happen is if we went back and used the quadratic formula, we would get back to these being our roots. So now let's look at one more. So we're going to have a polynomial of degree 4 with coefficient zeros that are 3 minus square root 7 and 4i. So that means we're going to have x minus 3 minus square root 7, x minus 3 plus square root 7, x minus 4i, and x plus 4i. And what I'm going to do is I'm going to do each of these. We're going to kind of work them in pairs here and then multiply our products together because it's going to be a lot. So let's start here with x minus 3 plus square root 7, x minus 3 minus square root 7, and that's going to be x negative 3 square root 7, and x negative 3 negative square root 7. So get x squared negative 3x negative x root 7, negative 3x, positive 9, 3 square root 7, x root 7, negative 3 root 7, and negative 7. And so canceling out this and this to get x squared minus 6x plus 2 on that side. And then over here, we're going to have x minus 4i, x plus 4i. We get x squared minus 4ix, 4ix, and 16. Those cancel, so we get x squared plus 16. And now we can multiply and find the product of these two numbers. So we're going to have x squared and 16. X squared, negative 6x, and 2. So we get x to the fourth, negative 6x cubed, 2x squared, and 16x squared. 6 times 16. I gotta cheat. We're gonna go to Desmos. 96. There we go. 96x, negative 96x, and 16 times 2 is 32. And now we are going to combine all of our like terms, which in this case we don't really have any. So we have x to the fourth minus 6x cubed plus 18x squared minus 96x plus 32. And there is our fourth root polynomial with all of those imaginary roots. So I hope this makes sense. We will, of course, be doing more practice with it. And this is a really long video.